Good morning, ladies and gentlemen. It's my honor to deliver this fellow lecture. My topic will be nano-enhanced membranes. So I'm going to share a little bit about my experience with how to use nanotechnology and biotechnology to make better membranes. Now, we know that water scarcity is a grand challenge in the world. So in many parts of the world, for example, in Africa and the Middle East, Southern California, there's very limited water. And a lot of these places, they are doing desalination. They trying to use membrane technology to convert seawater into fresh water, into drinkable water. On top of desalination, in many places, people are also using water reuse. So for example, in Singapore, the place I stayed for nearly 20 years, what they are doing is they collect wastewater through this kind of deep channels, and they centralize the wastewater, and then they treat wastewater with a process called reverse osmosis. And if you look at in Southern California, the same thing is happening. People take wastewater, the treated wastewater goes through a series of processes, including microfiltration, reverse osmosis, and advanced oxidation. But if you look at all these processes, whether you're talking about desalination or water reuse, the key, the heart of the technology is reverse osmosis. Now, reverse osmosis actually is a very old technology. So if you look at where reverse osmosis started, it's 1959. The first reverse osmosis membrane was demonstrated. And the current kind of a membrane we are using, so-called polyamide thin film composite membrane. Now, this membrane was invented 40 plus years ago. So 40 plus years ago, we invented this membrane, and today we're still using the same kind of materials. So the question is, can we do better? If you look at existing commercial membranes or existing polyamide membranes produced in the labs, there is obvious trade-off behavior. When you increase the water permeance of the membrane, the selectivity of the membrane decreases. So this is a relationship, we call it upper bound. The upper bound trade-off. When you have a more permeable membrane, it becomes less selective. Now, in recent years, there's a lot of interesting materials has been surfacing up. So for example, people talk about aligned carbon nanotubes. Can you align carbon nanotubes and to make it for water desalination? About 15 years ago, there have been a bunch of publications in Nature and Science talking about this topic. Of course, people quickly realize it's not so easy. So in this diagram, the horizontal axis, it basically shows the scale of development. When we say full scale development, that means this technology has already been adopted in the industry. And unfortunately, aligned carbon nanotube, because it's very difficult in terms of scaling up. So the vertical axis scaling up. So the current scale of development is still miniature. We can only make millimeter square of membrane area. Even though the potential of this technology, if it's successful, the performance can be very promising. So in this diagram, just to remind you that the size of the circle is used to indicate the potential breakthrough. Another interesting material is called aquaporin. Aquaporin basically is water channel proteins. This is a very fantastic material, very permeable, highly selective. But then again, when we look at the scale of development, it's still at bench scale, between miniature scale and bench scale. On the other hand, these are some of the conventional existing membranes, already commercialized. Now these membranes, their performance is limited, but their scale of production, they can be easily scaled up, they can easily produce at large scale. So the question is, can we find a combination? Can we find a combination that the membrane has a very good performance in terms of this water permeance, and selectivity. Can we find a membrane somewhere in this quadrant while we can still mass produce it? So this is the aim. I'm trying to convince you, yes, through use of advanced nanotechnology, biotechnology, we can do something better. So in my talk, I'm going to talk about two different things. So one is aquaporin-based membranes. How can we use biotechnology incorporates proteins, water channel proteins in a synthetic membrane and make a fantastic membrane. And the second part is to use nanotechnology to enhance membrane performance. All right, now first about aquaporin. Aquaporin, the nickname is water channel protein. Water channel protein was awarded the 2003 Nobel Prize in Chemistry for Professor Peter. And basically this protein, it's kind of interesting. You have this kind of defined pores. This pores, the narrowest restriction is about 3 angstroms. So that size just is good enough for water molecules to pass through the membranes, not even for proton. And there's some kind of a positive charge at these two sides, which forces water to orient with its oxygen atom towards this positive charge. And inside this water channel protein, water molecules will form a line, a stream of water molecules, and they can quickly, they can pass through this the channel inside the protein without experiencing much friction. So this makes the transport of water highly efficient. Now, if we do an comparison, here is a paper published by Manish Kumar in PNAS. They compare this synthetic membranes, the existing commercial RO membranes, with aquaporin-based membranes. So here we see there's 2 orders of magnitude. The nature has this kind of proteins, which is orders of magnitude more efficient than our current synthetic membranes. Can we do something with this kind of naturally available protein to synthesize a better synthetic membrane? So in my collaborators' lab, they have this bioreactor. They grow E. coli cells and then harvest aquaporin Z from E. coli cells. After you have the aquaporin molecules, proteins, you can go a series of further processing, such as freeze-thaw cycle and extrusion. Then you can make this kind of vesicles with uniform size. And one can also insert aquaporin proteins into the protein liposome, So at the end of the day, we can obtain this kind of protein liposomes. This is a lipid bilayer with aquaporin proteins inserted in the lipid bilayer. Now we can test the separation performance of this kind of small entities. The size of this protein liposome can vary. We can control its size by choosing the membrane we use for extraction. So for most of our experiments, we stick to 200 nanometer diameter. But anyway, we can finally control this the size of protein liposome. Now here we do some stop flow measurement. Without aquaporin inserted in the protein liposome, its change of volume under osmotic driving force, this volume change tends to be quite slow, which indicates this liposome itself is not so permeable. But once we incorporate aquaporin Z inside the liposome, here we can see this is a much faster response. And correspondingly, if we look at the liposome, the permeability of the liposome versus the permeability of the protein liposome after the incorporation of aquaporin Z, this permeability is increased by 2 orders of magnitude. at the same time, if we look at the rejection of NaCl, sodium chloride, the rejection is very good. We nearly have a perfect rejection of NaCl. So that's very good. This is a fantastic starting material. Now, in the literature, there has a lot of publications talking about how you can take this kind of liposomes then to make it into a synthetic membrane. So, for example, Professor New Chang's group has proposed that you can actually suck those protein liposomes onto a porous substrate. So you have this kind of vesicles sticking out, and part of this get into the substrate pores. This entity can be used to collect water. So because of its very high permeability, water can be collected through this vesicle and pass through these pores. Or another way you can spread this vesicle into a planar layer, biplanar layer. This is a process called vesicular fusion. And you can also prepare this kind of structure with aquaporin assembled in this bilayer and spanning over the pore in the substrate. Now, the problem of this kind of approach is that, again, you cannot scale it up. When you make meter squares of membranes, you encounter a lot of defects, and the long-term stability of the membrane is always a very big challenge. So in our lab, we decided to do something different. We take the vesicles, and we incorporate it into a salt rejection matrix. So this matrix itself can remove some salt, but the vesicles are used as a fast transport paths to conduct water, to quickly conduct water through, but they can reject sodium chloride or other solutes. So in this approach, you can enhance the water permeance as well as enhance sodium chloride rejection. So basically, we take this idea, we demonstrate that we can do it. This is SEM cross-section of the membrane. Here you can see this kind of vesicular structure embedded in our matrix. And basically, we patented the idea, we made some commercial products. So this idea has been taken by a startup company, Aquaporin ASA. And here you can see after further optimization, they can incorporate much more protein liposomes in the membrane. And the company has won quite a lot of awards and has been well recognized. They got a lot of funding for further research and scale up. Now the product is already available in the market. So pretty happy to see that. My next part of the talk will be on how to use nanotechnology to enhance membrane performance. Now, one of the ideas we have is that traditional traditional reverse osmosis membranes, if you look at the rejection thickness, it typically has about 200 nanometers plus minus. Now, so our very first idea is, can we make a much thinner rejection layer? How about a few nanometers? If we can make it down to a few nanometers, then obviously we can get a much more permeable membrane. Now, the conventional way of making polyamide membrane is you mix two monomer solutions and you don't have the control. So here we come up with the idea that maybe we can use additive process, something like additive manufacturing, or in a recent paper in Science, they call it 3D printing of polyamide membranes. I mean, the word 3D printing is somewhat arguable, I would say, but for those of you who are interested, you can look up 3D printing of polyamide membranes. It was published 2 years ago in Science. Anyway, our paper was published before that paper. We have a pretty similar idea. What we can do is we can electrospray the monomers instead of let the monomers meet at bulk solutions. Instead of you mix two bulk solutions, we can spray those solutions into micro droplets. Once you split this, then you can finally control the amount, the mass of the monomers you deliver for this reaction. So by finally control this, we can actually, for example, we can use the split time to control the membrane thickness. So for this particular membrane, we made it down to, for example, 10 nanometer, but indeed the thinnest membrane we made was 4 nanometers, a continuous film, a continuous rejection film, 4 nanometers. So this kind of a process is interesting. It allows you to have a very good control over what you want to make. The problem is that this reaction time, now in traditional membrane fabrication, we're talking about a few seconds, but now we extend the reaction time into minutes or even hours. So in terms of commercial production, again, this makes the technology less competitive. Can we do it a bit better? We can still use, we can still rely on the conventional reaction. So in the conventional reaction, we have these two monomers. This is called N-phenyldiamine and trimethyl chloride. These two monomers react with each other. They form this polyamide. Now, in the previous example, you see this film is a planar film. But what if we create a so-called nanoformed structure? What if we create a nanoformed structure? We're trying to introduce bubbles. We're trying to introduce nano cavities inside this film. Now, once we introduce this kind of nano bubbles inside the film, then we can create a lot more filtration area. So here we do a little demonstration. We use this kind of monomers, we create a condition, and here we see, yes, we can create gas. So now the idea is that if we can somehow, in this reaction will produce an acid and will produce a heat. Now, if in this reaction, if we can also provide some precursor, for example, one simple thing you can add is bicarbonate. If you can add bicarbonate in that reaction, you add bicarbonate. Bicarbonate receive a proton, and under heating that releases CO2, and those CO2 bubbles turns out to be in the range, their size is in the range of 20 to 100 nanometers. So then we can create this kind of nanobubbles inside this rejection layer. So here you can see, this is our control membrane. It has a smooth surface. If we add this CO2 precursor, we create this kind of rough surface. Basically, these structures contain this kind of bubbles. Or another way to create the nanobubbles, you can use ultrasound. You can use ultrasound to create the nanobubbles. Again, you see similar kind of surface morphology. Now, this is fantastic because a very simple chemical, cheap, simple chemical, you add into your recipe, and here we can see our water permeance is greatly increased. We can greatly increase the water permeance, and interestingly, the rejection of the membrane is also getting improved. So we get a membrane with simultaneously improved water permeability and rejection. There is one problem. There is one problem with this approach. If you create this kind of nano cavities, the cavity itself is not selective. The cavity itself is not selective. So basically, this method allows you to very efficiently increase the permeability. However, in terms of rejection, the improvement is limited. It's basically because the cavities are non-selective. So can we do something better? Now, so previously we were talking about nano cavity on the size range, on the length scale of 100 nanometers or several tens of nanometers. If we can reduce this length scale down to a few nanometers, then we can create some more selective nanochannels. So in this case, in this particular example, what we do is that we incorporate a hydrophilic nanoparticle. For example, you can grow silver nanoparticles in situ by just reduce the silver ions in situ to form the nanoparticles, and then you can form the interfacial polymerization of the two monomers. Now it happens that if you have a hydrophilic nanoparticle, this nanoparticle will hydrolyze one of the monomer. So this kind of hydrolysis will prevent the growth of the material, the polyamide, around this particle. And that will create a finely defined nanochannel. And here you can see this is our silver nanoparticle with the nanochannels around it. This size, the gap of the nanochannel is on the order of 2 to 3 nanometers. And because of the silver nanoparticle itself contains negative charge, so with the electrostatic interaction or donor effect, you can use this effect to enhance the rejection of sodium chloride, and as well as some other toxic organic pollutants. So this is a very simple method and very effective to not only increase water permeance, because you have this additional channels for water to get through, but at the same time, because of this channel is so thin, it's selective, it helps you to enhance your selectivity against micropollutants, toxic pollutants, and sodium chloride. Now, again, you do have some challenge because the size of those kind of selective channel is very difficult to control. If the size is in the range of 2 to 3 nanometers, these are effective. But once the size gets down to 10 nanometers, those channels become less effective in selectivity. So we want to create a more controllable method to make our membranes, and again, to allow us to mass produce this kind of membranes. So one easy way, in the conventional way, you make a membrane, you make a polyamide layer on top of a substrate, a porous substrate. Now what we can do is introduce another microporous interlayer. Actually, you have a lot of different choice. So for example, we have tried polydopamine, or we can use the complex between ferric ion and tannic acid to construct such a layer. So we can finally choose the thickness of this interlayer, and on top of that, then we can grow a polyamide rejection layer. Now, after we do this, we realize a very interesting phenomenon. We look at the water permeance. The control membrane water permeance very low. After we incorporate this additional interlayer, the water permeance is increased by almost 10 times, an order of magnitude enhancement. And this effect is really explained by this so-called gutter effect. This layer, the microporous layer, serves similar role as this water channels. So this microporous interlayer is highly permeable. So it allows water to very quickly channel through this selective microporous layer. At the same time, this intermediate layer is also selective against our pollutants, our contaminants that we want to remove. So the combination of that makes our membrane fantastic. An order of magnitude enhancement in water permeance, and at the same time, and major enhancement in salt rejection. Now, by including this layer, actually, we can also simultaneously create this kind of additional nanobubbles to achieve some further enhancement in water water permeability. And this method can be very easily incorporated in our existing commercial production lines. So I look forward in the next couple of years, I look forward to commercialize this technology. Now, without further doing, I was just trying to summarize that it's a very interesting journey. If you look at the traditional approach, over the last 40 years, nothing has happened. We are still using the recipe developed 40 years ago. But if you look into the nature has much smarter solutions. They use water channel protein aquaporins to deliver water at extremely high selectivity and very, very high water permeance, which is 2 to 3 orders of magnitude higher than our commercial counterparts. So there is a lot of room. There is a lot of room for us to develop much better membranes than the existing commercial membranes. So I shared with you the use of aquaporin proteins, and indeed, if we use nanotechnologies, we can use nanoforming to create additional voids. Unfortunately, those voids created are non-selective, but we can, by reducing the length scale of those channels, we can eventually create more selective channels. So you can either create interfacial channels. You can also use those porous materials which have intrinsic channels, or you can use interlayer, which is microporous, that contains a lot of water channels. Those channels are also selective, and we have demonstrated an order of magnitude enhancement in water permeance, at the same time major enhancements in membrane selectivity. So with this, I'll end my presentation here. I thank my funding agency to provide me sufficient funding to do what we are interested to do. And yeah, so thank you very much for your attendance. If you are interested in my talk, and if you have any further discussion with me, you can always email me. I'm ready to answer your question. Thank you.